Welcome friends. Today we shall derive the one-dimensional continuity equation. The continuity equation is based on the law of conservation of mass. So let's understand what exactly we mean by the conservation of mass. So suppose we have a system. So this is a system and the mass of the system is m. So if the rate of mass entering into the system is m dot in and the rate of mass leaving the system is m dot out. M dot in is basically the amount of mass entering into the system per unit time, while m dot out is the amount of mass leaving the system per unit time. So by law of conservation of mass, we cannot create or destroy the mass. So whatever mass is entering into the system per unit time and whatever mass is leaving out of the system per unit time must be balanced in terms of the mass of the system. So if the amount of mass entering into the system is more and the amount of mass leaving from the system is less in the given time interval, then that mass should be accumulated in the system. Similarly, if the amount of mass entering into the system is less and the amount of mass leaving out of system is more, then there must be the reduction of the mass in the system. So the conservation of mass talks about the balancing of masses which are entering into the system, leaving out of the system, as well as which are stored in the system. We can write down the conservation of mass for this given system as the rate of mass entering into the system, which is m dot in, minus the rate of mass leaving out from system, that is m dot out. So if the rate of mass entering into the system is more and the rate of mass leaving from the system is less, then the mass will be accumulated in the system, that is the rate of change of mass of the system. So it is changing with respect to time, so this we write as the rate of change of mass with respect to time, that is dm by dt. This is general mathematical expression for conservation of mass. Therefore we can write down m dot in minus m dot out equals the rate of change of mass of the system with respect to time. So you have to understand, very important note, that a steady state condition, the mass of the system does not change with time. So in that situation, dm by dt is going to be 0, that is mass is not changing with time. Then this equation, which indicates the conservation of mass, will be modified as the rate of mass entering into the system is same as the rate of mass leaving from the system. So for steady state condition, you will get m dot in, that is mass entering into the system, must be equal to the mass leaving out of the system. So this equation is very important, that is m dot in equals to m dot out. Now, having understood the concept of conservation of mass, so now we would like to derive the one-dimensional continuity equation for a fluid flowing through a pipe. So we are going to consider a fluid flowing through a pipe. So suppose this is a pipe. So we have a fluid flowing along the length of the pipe. Now, so by using the law of conservation of mass, we would like to derive the continuity equation for this particular situation. So let us consider a particular section of the pipe. So fluid is going to enter across this section, okay. So here fluid is going to enter into this particular pipe with velocity v1. So fluid is entering across this area of cross section of pipe with velocity v1 as shown in the figure. You can see here. Now this is the section 1. So the area of a cross section of pipe at this particular section is a1. So while passing through this particular pipe, the fluid is going to exit from a particular section. So if I take this section, so let's say area of this section is a2 and fluid is going to leave out from this section with velocity v2. So the fluid is entering into this particular pipe across this section a1 and fluid is leaving from this particular pipe across section a2 with velocity v2. The fluid has velocity v1 at the entrance and fluid has velocity v2 at the exit. Now if I say the fluid has density ρ1 at this section. So fluid is entering with density ρ1 at this section, while fluid is leaving with mass density ρ2 from this section. This is section 1, this is section 2. So fluid is entering with velocity v1 and density rho 1, mass density rho 1 at section A1, while fluid is leaving with velocity v2 and density rho 2 from section A2 of the pipe. So we can assume this particular portion as system, and we can apply the law of conservation of mass to this particular system, and we can find out one-dimensional continuity equation. So let me write down these things. So v1 and v2 are, we can say, average velocity of fluid at entry and exit respectively. Rho 1 and rho 2 are the mass densities at entry and exit, while area A1 and A2 are the area of cross section of pipe at entry and exit. So we are going to assume steady state condition. The rate of mass entering into the system must be equal to the rate of mass leaving out from the system. But we know that the amount of mass entering into the system is given by m dot in, the density at the entry point, area of cross section at the entry point, and velocity of fluid at the entry point. While the rate of mass of fluid leaving out from the section 2, that is m dot out, is the mass density at the exit point, area of cross section at the exit point, while velocity of fluid at the exit point. This is a very important relation. We have already derived this relation, which is mass flow rate across a section, in our previous video. So kindly go through that video and you will understand how to get mass flow rate, that is m dot equal to density into area into velocity. So we shall be getting from here rho 1 A1 V1 equals rho 2 A2 V2. It means the product of density, area and velocity at section 1 is same as the product of density, area, velocity at section 2. That is, mass flow rate of fluid at section 1 is same as the mass flow rate of fluid at section 2. So this we can say that mass flow rate at each section of the pipe is going to be same. Therefore, we can say that density into area into velocity, that is constant at each section. So this equation is the continuity equation in one dimension. There is a very important note here, that is, so if fluid is incompressible, friends, the density of fluid at the entry is going to be density of fluid at the exit. So in that situation, your equation would be simplified as area into velocity equal to constant, because both sides of the equation the density is same, so we can cancel out density from both sides. So we will only get area into velocity equal to constant for incompressible fluid. So this is the second form of one-dimensional continuity equation, that is area into velocity, which is also known as discharge, equal to constant. So this is also very important. This is called as one-dimensional continuity equation for incompressible flow, and this is one-dimensional continuity equation in general situation. So like this, we can derive the one-dimensional continuity equation by using the law of conservation of mass.